ladies and gentlemen. Very welcome to the NeIC 215, and you're very welcome here. And my name is Mille Milnert, and I have the honor to be the chairman of the opening session. And I'm sure that will be a very interesting session, since we have an impressive list of very qualified speakers. My background and interest in this area comes from a number of positions that I've held that are related to this field. I've been the chairman of the National Supercomputing Center at Linköping in Sweden, and I've been the rector of that university, and also I've been the chairman of the SUNET, the Swedish University Network, and also I've been the director general of the Swedish Research Council, and presently I'm the chairman of the SNIC board, the Consortia for Supercomputing Centers in Sweden. So for a long time I've had an interest in this area. And first of the speakers in this impressive list is Dr. Rita Maila, who is the leader of the Science Policy section at the Department of Higher Education and Science Policy, Ministry of Education and Culture in Finland. And that is a very important position, since she is in charge of developing strategies and also of implementing them. And she has worked in a number of positions and committees and organizations, both within Finland and within Europe. And also she is chair of the strategy group for the open science in Finland, which is also, of course, a very important position. So please, Dr. Maila, if you would come up and see if we can get this. Yes.
Okay, thank you very much for the kind introduction, and really I'm truly honored and delighted to be able to welcome you all on behalf of Ministry of Education and Culture to this event in Helsinki and in Hanasaari. And I know you have already had 2 busy days, but I'm sure you will have very good continuation of the whole conference in here. We're very proud to have you here, because we are also very proud about this area, what happens in Finland, and Nordic collaboration is essential to support also our national initiatives here. I think I'd like to start from the musicians, comparing musicians and researchers, because they have many similarities. They are all enthusiastic about their work, and when they start the project, they might know what the end result will be. And they are also people who have been trained and need support in their own work. And if you think about all the changes happening in music business in the last 3 or 5 years, it's immense. We have seen iTunes, we have seen Spotify, we see decrease of CD sales, and we see that actually the whole business is changing in a very, very short time period, which I think hardly anyone could have been forecasted. And the reasons for these changes are actually globalization and digitalization. And I believe those two are the same things which challenge researchers' life today. The globalization is really, we are already in the global market for services and skills. That's a reality. The best people get recruited in the best places. And we need to ensure that also in our countries we have best services, best skills available for our needs. And therefore the key question is actually, what is the Nordic path in global evolution? How can we sustain the development of society and business in the best way? And digitalization, I would like to claim it changes everything. It has provided us for new ways for exploring scientific knowledge. We have seen the emergence of large-scale international infrastructures, which provide us tools to find something we never could have found 10, 15 years ago. But it also changed how we exchange information and knowledge. And when we combine both of these, how to create new knowledge and how to exchange that, it changes not only things which concern ICT, but it changes the whole culture. It changes our processes, how we work or should work. It changes our activities, and gradually it will also change how organizations will look like. And therefore, the question is again, how we can best benefit this digitalization era. So these two phenomena are the founding principles we have to look for when we look about open science, open research in Finland or in global level. And therefore it's not surprising that Commissar Günther Oettinger has said Europe's future is digital. This is something we hear a lot everywhere, and I think this is very important to take into account. There are three issues. First is to provide better access for consumers and businesses to digital goods, that actually online services are used across the borders, and there are few barriers for businesses. The second one is that we have to shape the environment and digital networks and services to flourish, and actually right rules and conditions are fundamentally important here. And third, there's a need to create a digital European market, digital economy and society. These are big challenges, but I believe this is the right way to go ahead. Europe has to take this situation very seriously and be very active and proactive in decisions and support decisions. In Finland, we have a very good situation if you think about expertise. This is a digital economy measuring report of OECD, where we can see that Finland is next to the second one after Israel, when you look about percentage of researchers in business sector who work in information industries. It's over 50%. And this is, although a bit old now, 2011, it shows that we have a lot of capacity in this country, which is very good. We have a lot of ICT experienced people who can support us in this huge change what is now happening in the world. But it's not enough. We need good ICT supports, but they have to understand what is needed to get better results. But we also need to engage much more with users. And there are two types of users, those active ones who actually know how to utilize ICT tools. And I believe those are the ones who is easy to talk with ICT experts. But we also have basic users who should be engaged to understand how digitalization and ICT support and tools can actually fundamentally change the way of working, hopefully for the better way. Digitalization also challenges, therefore, the competence and support for the research process. In the old way, researchers wrote a paper, it was published and distributed by publishers for the end users, whether they have been researchers or industry, for instance. But now we have new ways, similar to the music business of iTunes and Spotify. We have open access journals, over 10,000 in the world. We have very new initiatives for open data and very well evaluated systems already in place which have been used and can be used. And researchers are also facing new social media opportunities. We have over 4 million people joining ResearchGate, where they can share not only publications but also their ideas and talk about science with people who they have maybe never met. So this all changes the processes of science, and we have to be vigilant to understand how this change will impact our actions. We have to think about costs, who will bear the costs, who will build infrastructures, what about IPR, what about visibility of science in national level and globally. So therefore we believe in Finland also that open science and research is something we have to take seriously, because it also has and can provide a lot of assets for us. It can actually fundamentally improve the possibility to increase the quality of science and verification. It can also provide totally new ways of collaboration across disciplines, across countries, and it can also therefore increase the impact of science, and not only within science but also for society in large. It can support lifelong learning, which is very important since societies are developing so fast that we have to have support for lifelong learning, and open science and research can provide there an excellent tools. It can also support innovation capacity. This is something we discuss, I think, every day in Finland nowadays, and there are lots of ways to explore more how open science and research can actually become a reality to support our innovation capacity more than today. And last but not least, we have citizens. In Nordic countries, we have a pleasure to work in a situation where our citizens trust a lot in science and research. Researchers are respected here. But But it's not the case in many other European countries, and if you go beyond Europe, even less. And therefore, open science can be used to create and establish trust for science, and also engage citizens to work with scientists to understand how the processes go. So there are a lot of hopes and wishes and realities what can take place when open science research is taken seriously in every country. In Finland, we have discussed open science research, and we have the roadmap 2015-2017, where we have discussed a lot what is open science and research. And it's really all the efforts which promote open procedures like verification and validation. And one important issue that is not black and white. It's not open everything or nothing open. It's something in between. And the reasons or the context which define this in between are the ethics in science and legislation and maybe agreements with business sector. So it's wise openness. We have to be sure that in everyday life, in future, researchers can be wise in openness, understand how to be open, when to be open, and what are the constraints or support they will get to support that one. The idea is to have the research results to be reused either by scientists, by decision makers, citizens, or business sector. We have 4 main areas in the Open Science Research Initiative, which are defined in roadmap. First is really for the science itself. We want to reinforce the intrinsic nature of science and research. Repeatability, openness, verification are important. We want to strengthen openness-related expertise. You cannot say you have to be open if you don't know what openness means. So therefore we have to ensure that expertise among the whole society, and especially scientific society, is increasing to the level this can become a reality of everyday life. We have to ensure that we have a stable foundation for research processes. We have to have good infrastructures which support the work. We have to have good services which are on a timely manner available. And last but not least, we want to ensure that this increases the societal impact of research for the whole society. So these 4 pillars are the ones which are ongoing now in our national roadmap, and we are working very hard with a great support of CSC with whole society, scientific society in Finland. But I think it's not only one country or each country who should work alone, but we should work together. And I think today this Nordic conference is one good example when you share your ideas and can talk to each other. We have 4 main strengths, I believe, in Nordic level, which actually facilitate that we can work together also in this area. We have actually national special features which support openness and research. We have equality-based research environment, and we all have high investments in R&D. The education level population is high, and science is appreciated. So it's a good place to work in this area. We also have a good track record. We have proven and still ongoing projects which have already beared fruit. For example, Nordic collaboration in networking Nord-Net and also Nordforsk. They work well. So this is a good starting point and building position. And the third element, we can see we look for global areas in this area that actually Nordic influence is quite high. And when we work together well, we also can have more influence than one country alone in a global level. And that's very important, that the voice of ours is heard and influences on global decisions in this area. And last but not least is trust. It's difficult to work together if you don't trust each other. But in Nordic countries we have learned how to build, how to invest together, what kind of research infrastructures can be built together. So it's a good basis to start and continue the work. And therefore also when Finland will chair now next year the Nordic Council of Ministers, we have been discussing that one area would be open science and research because we have so much to build upon already now. And it's very important for every country. So to conclude, I believe that it's an urgent need and important for every government to take open science and research seriously, because we allocate a lot of funding for education and science now our local level. And as we have seen in music business, changes can happen in a few years, and changes we couldn't even expect. So it's not time just to talk, but it's time to act. And therefore we have to extensively involve the scientific community and to be able to build infrastructure, support and other activities for them and work with them and not only for them. But this cannot be done in local level. It must be done in local, national, and international level. And therefore, I believe, based on these Nordic good experiences, that this also is something where collaboration is very, very useful and will promote things much further than we could do alone. And therefore, I'd like to conclude by saying that NeIC can offer significant and valuable input, taking this one step further from local and national to the Nordic level. And I'm sure and convinced that you can do it. So very much welcome, and have a very nice and fruitful conference. Thank you very much.
For science, Dr. Kowski has worked in several positions in Nokia, the Nokia Research Center and the Nokia Technology Platform. And he also worked in various positions in both Europe and within Finland. He has a PhD that was written about meta-computing technology. So, please, see if I can fix this one.
Yeah. Thank you very much. Is this stuff on? Okay, that works. Okay, thank you very much. It's quite some time when I was working in Nokia. That was when Nokia was still doing okay. So nice to see so many people you found here despite all the fog. So I wonder how many people are there in the next conference center 2 kilometers west from here. But anyway, so on behalf of myself and CSC also, I would also like to wish you welcome to this great event. I know some of you have been here already for a few days. You know, this is a very good time to organize events here in May in Helsinki. It's usually very warm and hot weather with sunshine. And well, actually we have a long history of climate data, so it actually proves that a couple of years that was the case in somewhere back in the 18th, 19th century. So anyway, I would also like to start to congratulating those people who were actually on Tuesday taking this canoe trip, because there was such an event after the conference, canoe trip. So I wonder how fast did you need to paddle in order to avoid canoe being frozen into the sea. So, but anyway. To start with, welcome to Finland. Spring is now here, as you can see, and deers walking in the field like this. So, okay, back to the real business. So many of you know already about CSC, and so I'm not going to give a long talk, also since I don't have much time allocated here, but within the next 5 minutes I would like to just to point out some of these things here, and give some kind of actual information what we are doing today and how we are established. Today, as many of you know, in Finland it's a centralized model, so everything is centralized under the same roof. So today we are a bit more than 270 people here. Most of the people are here close by in Keilaranta. It's maybe this 2 kilometers, 1.5 kilometers from here, and some of these people in our office in Kajaani, almost 600 kilometers north from here. Okay, so wrong side. So today, during this, or let's say during this week, I'm sure we are talking quite a lot about research infrastructures and commonalities between the Nordics and also beyond. And here are some of these acronyms we are participating. Actually, you can see, if you can see there in the low corner, that NeIC is actually a research infrastructure, or at least mentioned in the Finnish, has an entry in the Finnish research infrastructure roadmap. So this is pretty well known and mandated project or initiative here in Finland. There are some others too, which we recently upgraded this roadmap here, and you can see There are a number of entries. CSC is involved as a coordinator in many, a couple of those, and then we are some kind of partner in many of those too, because we try to promote the ICT synergy between the research infrastructures. And then I would say that in most of those which are not market, CSC is somehow involved in discussion, or we have a collaboration going on here. And I think this thing is going to develop, and many of these things you see in this list of many of these acronyms are something that is a larger interest among the Nordics. So I hope we will use the opportunity to discuss those collaborations during these days here. So same applies to the EU projects. There are a number of those, and it's nice to see that, or actually note that in many of the e-infrastructure European projects, there is a number of Nordic countries involved. So we have a good collaboration with our counterparts in other Nordic countries, in addition to the real Nordic projects like NeIC. So one of them, to mention separately, is just started, the second EUDAT 2020, 33 European partners. Now it has been growing, and this is very much involved with the data infrastructure, so data management, how to utilize data, how to make these things work better. And now I think this is one of the highlights of this coming project portfolio. So it just started and going to continue now for three more years. The budget is 19 million from NeIC, so it's quite a big activity, and I think the links between the work that's done in the NeIC and what's done on the EUDAT, partly also overlapping. There are same people even working in both acronyms, so that is something that's gonna also develop in the future. That's only one example. There are a number of other projects, and you're gonna hear more about those also during this week. To mention this, I mentioned that part of our people are a bit north. I know that some of the people took today the morning jogging, and actually passed by the CSC office. Well, I heard that some of the people took the morning jogging. I wonder why, but I mean some of the people did it, and they passed by the CSC office there 1.5 kilometers away. So if you have an extreme run morning jogging, you can pass also by our Kajaani office. So then you need to run a little bit further, but it's there up north really. That has been now in production for 2 years, and so we are extremely happy about that, and it actually have proven to be very efficient. This is one of the Nordic strengths also, this data center area. It doesn't apply only to Finland, as you know. It's also very valid in other Nordic countries. So collaboration related to that could also be increased, in my opinion. So some of the people say that PUE is just one figure. Well, the PUE, which describes that how much actually electricity used for other things than this real actual machine, like cooling, etc. So in Kajaani, our cooling method is basically that we open the windows, so it doesn't require much electricity. So now I think the newest figure from last year is 1.04. Well, PUE is not everything, but it's something. So I would say that already from our own data centers, which are quite modern also here, we save some amount of money for electricity only. So I think this is a topic that is discussed in a Nordic level, but could be discussed a bit even more. So I present this because it's one of our major projects at the moment where we are involved in, and discussions collaborating related to that are mostly welcome, of course. Most welcome. So to conclude this very brief overview, so in Finnish model we have this combined system. Our people here who are collaborating and actually participating in this workshop are happy to discuss many areas of e-science and science in general, and we'll do it from networks to application development and everything in between. So this is Nordic conference. So it's, to finalize, or let's say to conclude this short welcome, just present one slides where at least a couple of opportunities we can do together here, or we should do together. Some of them we are already doing, but growing the volume and growing the intensity, I think, is a good idea, because most of these things are such that everybody does it in their own premises, so why not increase the collaboration and maybe even save some effort and use that saved effort in some other means, like promoting the science and so on. So these research infrastructures are mentioned. There is enormous potential of increasing collaboration in Nordic level, together with NeIC and the centers in different and the research in infrastructures in different countries. Well, in addition to that, of course, the infrastructure side, many of us are running the same systems, or same kind of systems, developing same kind of software, and so on. That's obvious target. Decision making, we have been collaborating among the Nordics in many European bodies in such a way that 4 or 5 countries actually have a better weight in their voting, or let's say, or opinion presenting their opinions than one country alone. That has already been successful, could be increased. My favorite topic actually in this, which I think there is a quite fast benefits available, is this joint education and training. So why don't we do more courses or education programs together for e-science and so on? And there are many others, like software development, and say. But to conclude, I would say that we can do much more than we do today. So finding if we do it correctly, so looking towards the complementary solutions, and I mean building on top of what we are doing in each of our countries, not necessarily replacing it, but building on top of it and adapting it to different systems that we are running. So there is a lot of potential for more collaboration. I hope this week and this conference will promote that further. Thank you. Almost 10 minutes, I think.
Thank you. Yes. 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 Yeah. So, our next speaker is Dr. Gudmund Höst, who is the director of the Nordic E-Infrastructure Collaboration. And he also been before that, he's been the special advisor to the Research Council of Norway in the field of e-infrastructure, e-science and computational mathematics. And he worked in various positions in the Nordic Veritas, for instance, and also he's served as many positions within the Nordic organization and the European organizations, and he has a doctorate in science, mathematical statistics, both from the University of Oslo. So please, Dr. Höst, see if I can. Yes, that's the one. Okay.
Thank you, Mille, and thank you, Rita and Kimmo, for very welcoming words. And thanks to Finland and to Espoo and to CEC for having us here. A lot of people have contributed to this conference, and I intend to get back to that later today. For now, I think within this time scope, I would just remind you of this hashtag that you probably have not been able to avoid seeing. So there's a Twitter contest going on. There will be prizes. There will be a survey on this conference, electronic survey. There will be prizes, and all prizes will be handed out at the end of day 2. If you're not here until the end of the conference, you will not be able to get any of these prizes. So that is the main message here. Now Kung Fu. This is Bodhidharma. he was an Indian prince who went on a pilgrimage from India to China in the 6th century. He went barefoot across the Himalayan mountains, and he came to the Shaolin temple in China, and he was not admitted entrance by the head abbot there. So instead he went into the Song Mountains to meditate for 9 years, and after 9 years he was finally admitted into the monastery, the temple. And what he found there, the state of these monks, it really appalled him. They had been meditating for years and years, doing no physical exercise, so they were in a terrible state, really frail and in bad shape. So he ordered exercise. Every morning they had to gather up in the courtyard to do exercises, and he would chase them. He would find their hiding places, chase them with a stick. You have to go to the courtyard to do exercises. So this went on and on for some time, and one morning he couldn't find them. They were not in their usual hiding places, and he looked everywhere. So finally he gave up. He went to the courtyard himself to do exercises, but there they were. Everybody had gone there now voluntarily because they had undergone this transformation of the mind. They had seen that exercise is good for you, you need this. These exercises were then the seed for the martial arts that many of you know. And Kung Fu is not about fighting, it is about the learning process. So any learning process that requires energy, patience, and time to complete has this Kung Fu. So there's a Kung Fu of kayaking, a Kung Fu of running and cooking, and there's a Kung Fu of doing Nordic infrastructure collaboration. So this is about the learning process. And one of the first things you need to learn is the milestone of the Helsinki Treaty of 1962, a milestone of Nordic collaboration, sometimes referred to as the Constitution of Nordic Collaboration. And it has in its Article 12 about cooperation in the field of research, that it should be organized so that research grants and other resources are coordinated and used in the best possible way, including the establishment of joint institutions. And one example of such a joint institution is Nordforsk. It was established 10 years ago, happy anniversary, and it is owned by the Nordic Council of Ministers. What does that mean? Well, if the owners are the ministers of education and research in 5 Nordic countries. These owners have appointed the Nordforsk board, consisting of representatives from the national research councils in 5 countries. And the aim of Nordforsk is to foster collaboration in research and in research infrastructures, and also fund joint initiatives in this area. And also Nordforsk is a major funder of NeIC. In 2015, Nordforsk funds NeIC with 10 million kroners, which is 44% of the total in-cash funding of NeIC. And NeIC gets additional funding in cash from 5 Nordic countries, equal shares from Norway, Denmark, Finland, and Sweden, and a smaller share from Iceland. In addition to this, we get in-kind funding from national infrastructure providers, from Nordic Elixir nodes, also from IceCat, and from some of the sites. What is then NeIC? So NeIC is an organization that was established in 2012 with the previous long history of NDGF doing Tier 1 for CERN and other exercises and other stuff. It was established as a unit of Nordforsk in 2012, and Nordforsk is then the hosting organization. It provides administrative services, legal services, and also the Nordforsk board appoints the NeIC board. So formally, Nordforsk is the owner of NeIC. The NeIC board consists of 2 persons from each country, one from the Research Council and one from the National Provider Organization. This was true until quite recently, because at the beginning of this year, the Research Council representatives announced that they wanted to pull out of the board. So they want to leave the strategy and the ownership of and governance of NeIC to the national infrastructure providers. So there is now a smaller, more focused board of NeIC, still formally appointed by the Nordforsk board. So Nordforsk then plays this role of funder and hosting organization. And I think we see here one of the maybe the first dilemma for the NeIC board is to sort of find out what should the relationship to Nordforsk be. Do we want NeIC to do we want Nordforsk just to be some sort of hotel that you book into and you pay for some services and then you do whatever you want, or do you want it to be sort of a strategic partner, owner, and be able also in the long term to seek strategic co-funding of Nordforsk? So I think, and then this is much a matter of how ambitious you want to be on the Nordic collaboration arena. So do you want to really be ambitious and try to harvest all possible opportunities for e-infrastructure collaboration that can support Nordic research groups? Then this is something different than trying to be a sort of a minimalistic thing that only has some services that you pay for. Another dilemma that I would like to point out to you is the dilemma of how you organize collaboration, because there are several stakeholders in this. Some of the major stakeholders are the national infrastructure providers, researchers, and NeIC. How should the collaboration go here? And how do we go about the learning process of finding out what the roles of the various stakeholders should be? So should NeIC only provide services and develop services and only relate to the national provider organizations? Should they relate directly to the researchers? What should the researchers do? They might be confused if they now need to sort of relate to both the Nordic level service provider or actor in addition to the national providers. How do we do this? I think this is something that we need to take seriously, how we do this. And I think it's very much a learning process that will require this kung fu. It will require energy, time, and patience to find out how to do this the right way. How do we nurture or build e-infrastructures, and what can we do about this in the Nordics, and what could NeIC do? There are historians who have looked into this. There's an interesting report from the National Science Foundation, a workshop held in 2007. They wrote the report, Understanding Infrastructure, Dynamics, Tensions, and Design. Yes, there are tensions in this. We should be aware of this, and we should, and it's not necessarily a bad thing, but you need to be aware of it, and you need to handle it in some way. Well, one of the things that they point to is that if you look historically on how infrastructures are created, they usually come in phases. It is created through phases. So there's first the precursor stage, where you have local systems, local control, and then at some stage, at this formation stage, these systems start to link into networks and networks of networks, going from local control to distributed control and coordination processes. And then there's a consolidation phase where you have gateways, standards, and things start to get operative. But it's a complex process. It's a modular and incremental process where you need to build on what is there. You adapt to local systems, local situations. Maybe take one system, adapt to another national condition, and you get one step above in that process. And an example of that could be the current Trygve project that we run in NeIC, where you have in Oslo had the TSD system for sensitive data, it is now being put into some Nordic context where the other countries can also look at this, make something that is maybe better in some aspects, maybe just adapted to national conditions, but some a little bit different. And then we have a context where you can share knowledge and learn from each other's initiatives. So the NeIC's value proposition is, I think, if you refer back to these stages, at the formation stage, to be a facilitator of technology transfer between the countries. And the Nordic countries have good traditions in this, in also other areas. So there's an educational reform in Sweden. The other countries look at that. They do something maybe a little bit different, little bit similar, and then you sort of copycat in this way. So we can help to introduce this adaptation to national conditions, different laws and so on, introduce variation and adjustment, and help nurturing infrastructure in this way. Another thing that NeIC do is to provide a social space for virtual teams. So we have the Nordic Tier 1 operations. What we provide is a virtual social space where people can collaborate in a distributed way, and this has worked successfully now for many years. We also provide a social space for the national providers' activities of common interest. You will hear more about the Nordic Federated Cloud project later today, which is an example of that. Also, service innovation for Nordic user communities. I mentioned the Trygve project on sensitive data. So we also have similar projects and hope to start similar projects within the environmental sciences area and other areas. We've had workshop sessions on this earlier today. This is from the Kung Fu Panda movie. A slight twist of that. If you recall that movie, there's a running theme, what is the secret ingredient of the noodle soup of Pooh's father. And when you get towards the end of the film, they discover the truth appears and there is no secret ingredient. So the secret ingredient is nothing. Everything is open. We don't have any secret ingredients in NeIC. We believe in full openness. Should there be any secret ingredient at all, it is snow. So we have tried to apply snow in the all-hands meeting this year, and we intend to do this again. So snow might be the only secret ingredients, but the principle is full openness on everything. We put minutes, all project results, everything out in the open for people to see. And as Kimmo said, if we work together, we can do a lot more. There's scope to do a lot more in the Nordic arena. So by moving from this triangle, golden triangle, to a golden collaboration, working together, we could lift the researchers to a higher level, unprecedented level, and making impossible research possible. Thank you.
So our next and last speaker is Dr. Paul Messina, who is the Director of Science at the Argonne Leadership Computing Facility. And is also Argonne Distinguished Fellow. And he guides the teams that support projects that use MIRA, that is the Argonne 10 petaflops EBM Blue Gene system. And he served as distinguished senior computer scientist at Argonne, and he also had positions at Caltech. And also I happen to know that he's a keen sailor. And it's very sad that he couldn't extend his stay in Finland to sail in the Finnish archipelago. So, please, Dr. Messina.
Thank you very much, Miller.
See if I can get you started here.
My consolation is today is so foggy I would not be able to go sailing safely with all those islands there.
Okay, now you're on.
Very good. Good morning, and thank you very much for inviting me to speak here. It's my pleasure to be in Finland for the first time. I will give you my personal view on trends in the high-performance computing environments. As you can see from the outline, I'll be talking about how I see things today at the high end of HPC, the trends due to technology of various kinds, what the next generation of systems will be like, and implications as to how they will be used. The term exascale has been used for the last few years. That's 10 to the 18th operations per second as a general goal. It's, of course, only one step along the way. There will be things beyond that. But some of the issues that have been talked about, I think, are important, and some not as important as people thought. So my version will be along those lines. And then I'll talk a little bit about performance portability, because we don't have homogeneous systems, and even from one generation to another of the same company's systems, there are enough differences that applications people and infrastructure, software infrastructure people need to worry about portability, and of course performance matters, hence performance portability. Let me start by saying a few things about where I work currently and where I worked in the early part of my career as well. Then I took 15 years out to go to Caltech and also CERN. So Argonne is just outside Chicago, about maybe 40 kilometers. As you can see, it's a fairly large campus. And as I will say momentarily, they're big facilities. So the Advanced Photon Source is an accelerator that has very intense X-rays. And it's an international user facility. There are 5,000 users a year. And so people from industry, from universities, from the United States and many countries come and use it. And then for those of you who can see it, in this building, the Theory and Computer Sciences building, we have the advanced, the Argonne Leadership Computing Facility, which is another user facility, this one for computing and other things. This is a chemistry building, physics buildings, nuclear physics, and so on. So, and we also have some deer on the campus. It's big enough. In fact, this used to be a hunting estate in the 1920s and 30s for a very rich person who bought 3,000 acres, several square miles, and imported deer from Europe. In fact, white deer. But the government took it over soon after the war. So the way that Argonne was created essentially is as a consequence of the first controlled nuclear reaction by Enrico Fermi and his team at the University of Chicago. So this is a drawing of the first Chicago pile. These are all, graphite bricks, many of them. And so in December 2nd, 1942 was the first controlled nuclear reaction. And after the war in 1946, Enrico Fermi led the effort to create a new national laboratory. This one, where you saw, outside of Chicago, not in Chicago, which is where this was. And the goal was for peaceful uses of nuclear energy. So a lot of the early efforts to design and build prototype nuclear reactors for electricity were at Argonne. So there are major user facilities. I mentioned two of them, and there are others as well. A lot of efforts in nanoscale materials, batteries for automobiles and other things, for example. But to me, it's an important indication of how far computational science and engineering have come, that a computer is a user facility in the same way that an accelerator of particles is. And so people who want to use our current system have to write proposals openly. Proposals can be taken from anybody in the world, so long as it's open science or engineering. Even companies can submit and do submit proposals and get time, but it has to be for openness. So I was very pleased to hear so much emphasis on openness in the early part of this morning, because in fact that's a key aspect of our facility and that at Oak Ridge National Laboratory as well. So in 2004 there was a law passed by the United States Congress that established this facility, which is implemented in two places, Oak Ridge National Laboratory and Argonne National Laboratory. And they're dedicated to open science, and they're supported by the Department of Energy's Advanced Scientific Computing Research Program. And we routinely have two different architectures so that it both reduces risk and also gives more opportunities for different kinds of computation. But these are dedicated to very high-end computing. So we, although they're very powerful, we give relatively few projects time on it, but each project can have a lot. So at Argonne this year, the average, the median, allocation to a project is 100 million core hours per year. There are some as high as 300 million core hours per year. So the idea is to give a good project that's planning to do interesting science or engineering enough time they can do something they couldn't do anywhere else. Just as you have accelerators or electron microscopes, which have special facilities and characteristics, so you can do research you couldn't do anywhere else. I won't go through all of the numbers on this, so you'll be pleased to know on this slide, but I'll mention one thing. Over 3 million hardware threads in this machine, and we do have applications that use the entire system for weekends at a time, 60 hours at a time, and that's only part. Then they do it several weekends to get their campaign done. We have smaller versions of the system so that people can try things out and not get in the way of the big applications. And very important, visualization, data analysis, and storage. We also dedicate a significant amount of resources to that, because unless you can understand the results, unless you can store them, then perhaps you won't be able to get as much out of the calculation as you would like. At Oak Ridge, there's a very different system. It's based on CPUs and general purpose GPUs by NVIDIA. So while we have 48,000 nodes, they have only 17,000 and then the same number of GPUs, but the peak speed is 27 petaflops, so 90% of which is from the NVIDIA GPUs. So the way I think of the HPC ecosystem, certainly the big computers are important, but at least as important are, as I already mentioned, the file systems, being able to visualize and analyze the data, people with the right expertise who are dedicated to supporting the big projects, as well as the new projects who are trying to learn how to use systems like this. Of course, you get into programming models and languages, community codes I'll mention briefly soon, libraries, so you don't have to each invent everything, workflow management, and many other things. And these are important today, but many aspects of those, as I will try to indicate, will be even more important soon. More detail on the people. You know, in our facility, of course, we have a very substantial and expert operations staff, and what people usually call user services to do documentation, training, and establishing accounts. But in addition, we have 3 teams that are dedicated. One, these are computational scientists who typically each have 3 major projects that they work with over a period of months or years. And that's important because these are people who understand the domain. You know, they are material scientists, PhDs, high energy physics, chemistry, and so on. So they understand the domain, they understand how to do computational science in that domain, and they're very familiar with our system. And they also act as an ombudsman so that the project, if it has any kind of a problem, can go to their dedicated catalyst, as we call them. Then we have about 15 of those full-time staff. The performance engineers typically, currently rather 6, and these also tend to have PhDs in the science, but they've gotten very familiar with every aspect of the hardware and the system software and the libraries, and so they sometimes get assigned to a project that wants to get much better performance. They might work for months with one project and help them get a very high fraction of the potential speed. So for example, 2 years ago, a project in materials science that was only getting on the order of 10-15% of peak speed using the entire machine came to Argonne, some of the developers, for 2 or 3 days, worked very closely with the performance engineers, and then remotely for another few months. They now have a full science application that gets 50% of the peak speed of MIR, 5 petaflops. And that's very high for an entire full real science application. And then we also have a team of visualization and data analytics experts who make sure we have the right software available and also work with the projects to help them understand the results. So one example would be in visualization, the adaptive mesh refinement people at the scale that a machine like MIR makes possible, it has become quite an issue to be able to visualize the data. And so our team, along with some colleagues at the University of California, Davis, and the University of Chicago, worked out a new approach to AMR visualization, and it scales comparably to regular rig renderers, and so it was feasible to be able to visualize quickly enough to be useful, at extremely high resolution. So those things can be as important as how many flops you get. Our user community isn't very large by design, but it does span essentially everything that you would think of in science, including biology. So you can see a breakdown last year of the biggest allocation program inside by domain that allocated 3.5 billion core hours. And you can see material science is pretty significant, physics, biological science, engineering, and so on. So to get time on our system, to get the biggest allocation, 60% is through this, and we have 35 such projects this year. And then there are some other ways to get smaller amounts. And the same is true at Oak Ridge. Now, programming models come into play because as hardware changes, so does the way that you can exploit all that parallelism. So MPI, of course, has been the way that almost all of scientific applications get parallelism. And that was pretty much all you needed. And so you can see that in this Cray XE6 at Berkeley, called Hopper, even today, MPI only is 79% of the use, and MPI and OpenMP is only 21% because of the characteristics of that machine. And that was true at Argonne in our predecessor machine, but now on our current machine, because there are 64 threads per node and a total over 3 million hardware threads, you see that MPI and OpenMP are at 56%, MPI and P threads 9%, and MPI only is only 20%, so quite a difference. On GPUs, of course, you have to use different models, and you can see it takes a while. This is the fraction of hours delivered using the GPUs on Titan. It takes a while to get the usage up, and now it's at around 50%. So that's part of the ecosystem that matters. So you have to have the software well implemented, hopefully, and the expertise on our system. Now, Argonne was, as it happened, one of the centers very active in the development of the MPI standard. And one of the good things that was done at the time is that as the standard was being developed, a reference implementation was being concurrently developed so that people could try out the ideas that were being put in the standard. So the result was, as soon as the standard was finalized, there was an open source version of MPI called MPitch that was available. And so all the computer manufacturers could take it, and initially did, and then they maybe optimized the implementation, but on day one you had an open implementation that everybody could get at. So openness indeed is very important to us. Community codes are one way that one gets leverage because, let's face it, these are complex machines to use. It takes a lot of expertise to even use somebody else's code, much less develop it. And so the fact that there are community codes, these are application codes in the sciences and engineering that are typically put together by a substantial group of people, and that being open, people from around the world can contribute to them. Now, the ones that are in the darker shade are ones in which our staff at Argonne has either deep expertise or in most cases is also one of the developers. And so we're very familiar with these codes. And so we have all these available, which gives us a great amount of leverage. And again, it's the principle of openness and collaboration so that you end up with a better code than if you just had one small group with no external contribution. And this includes collaboration with other countries. For example, GPAW, which should be here somewhere, although I don't find it immediately. Oh, there it is. In material science is developed jointly by a group at Argonne and a group in Denmark. And so it's really very much a joint project. So I mentioned technology affects high-performance computing. So the key thing is that starting 11 years ago now, the way that chips are manufactured using semiconductor technology, the speeds have not gone up for the clock speed for 11 years, and they will continue to stay flat. And it has nothing to do with Moore's law, because that's continuing to be in effect. Each few years you get smaller features. That's Moore's law. But the Nart scaling has ended, which has to do with how much electricity you need to put into the chip to get a faster clock speed. And it got to the point that the manufacturers felt it did not make sense to increase the clock speed. But because of Moore's law, you still have many more transistors available per square centimeter. And so what are you going to do with them? Well, you just replicate the cores, and you start putting on the same chip everything that was previously on separate chips, including some of the memory, very high-speed memory. And so you have chips that currently have hundreds of pieces to them that used to be separate. Now they're all on one chip, but running at the same speed, each one. So the only way you can get more speed for your application is to take advantage of more things concurrently. That means that since we, in science, always want more power than we have and more memory, we have to deal with more and more parallelism. I'll say something about the next generation of systems momentarily, but we estimate that for exascale, maybe 8 years from now, one node, one chip will have maybe 1,000 cores. So you'll have to work pretty hard to get that much parallelism out. Very powerful nodes. And because of memory costs and the cost of moving data, we'll end up with relatively smaller amount of memory for the compute power, which is not a good thing, but economics drives it. And people will try to counteract that problem by having more levels of memory of different speeds, which is good, so the memory will be there, but getting to it will be more complicated. Now, being old, I am guilty of thinking back on the past maybe too much, but very early in my career, I was using control data CDC 6600s and 7600s. A few of you may know what that means, but they had small core memory and large core memory, and one had to, as an application programmer, explicitly move data from one to the other, because of course the small core memory was faster, but it was small, and so you'd move things in and out, and you had things called overlays. Guess what? We're about to have to do that again. So as we were looking at our two leadership computing facilities a few years ago, one at Argonne and Oak Ridge, we had this very high-level analysis. We, thought, okay, so we've got the hybrid multi-core, such as Titan at Oak Ridge, and so it has GPUs, and so the next one is likely to also have multiple CPUs and GPUs, not that many nodes, but very powerful ones, multiple levels of memory, and so on. And in the case of these hybrid architectures, a coherent shared memory within a node. And then in the many core like Mira, still the same, tens of thousands of nodes with millions of cores, but homogeneous. Again, multiple levels of memory and self-hosted. So that's what we anticipated, and we issued a procurement. It's been, 2 years now, 2 years ago, and then last April we made our decision, and 2 systems, again, we want to have the architecture diversity, were selected and contracted for. One by Argonne, so our next system will be an Intel system with Cray as a subcontractor, and at Oak Ridge and also Livermore, which is a nuclear weapons lab, so it's not an open one, we'll be getting an IBM system with NVIDIA and Mellanox subcontractors. Now, each of them has a separate contract that we label NRE, which means non-recurring engineering costs. That's because we signed a contract for machines that actually have never been built yet, and parts of which were proposed but have not been fully designed. And so the non-recurrent engineering is a separate contract to the company saying, okay, you said you'd be able to do this thing with the memory, now we'll pay you extra to do this one-time thing. Once it's done, then everybody can take advantage of it, so future customers can buy it as a result of us having invested in a separate research contract. So these 2 came up, and this very busy slide I will only mention a few things about. We, in addition to the leadership facilities, there's one at Livermore, it used to be at Livermore, at Berkeley, called NeIC, which is more dedicated to only Department of Energy research, as opposed to Oak Ridge and Argonne, which are open to the world. And so whereas Titan was 27 petaflops, the next machine for Oak Ridge will be about 150. Mira is 10, our next machine will be 180 petaflops. And one good thing is that even though it's a factor of 18 more flops, it's only a factor of 2.7 more electricity. So you can see that you're much more efficient for electricity usage, so that the and a little bit over 50,000 nodes, and quite a large file system, 150 petabytes with over a terabyte per second transfer. Why? Because of the issues that I mentioned. Data, storage, and movement are extremely important. Now within Argonne, because our next system, which is called Aurora, is not due until 2018, that's 3 years from now, we're going to get next year a small system that's a precursor to Aurora, not exactly the same, but along the same lines of architecture. And so we will have that initially for the transition, so that our users can get used to the new software environment, the new architecture. But then as that phases out, we are planning to use Theta, pretty large machine, as our data analysis and visualization system coupled to Aurora, the bigger 180 petaflop system. So again, we dedicate a lot of resources to the data aspects. The software stack is I shouldn't say it's a mess, it's complicated. You see the shading that, a reasonable part, this kind of shading is open source based software. And then there's a Cray software, the lighter blue is Intel software, open third-party software is this kind of yellowish brown, and then completely open source are the ones outlined in green. So a lot of stuff there, a lot of choices of compilers and libraries. So at least there is software, but it's going to take a while for people to get used to it, I think. However, I am optimistic about it. That was for the Argonne part of the next systems. For Oak Ridge, it'll be this IBM NVIDIA Mellanox system with only 3,400 nodes, which means that each node is something like 40 teraflops, extremely powerful nodes with a substantial amount of memory, but a huge amount of flops. So definitely a different system. And so based on that, people still keep asking me quite often, well, what's exascale going to be like? Won't it be dramatically different? And my answer is absolutely not. There's no way that I can conceive that in the next generation, after 2018, it'd be 2023, is what we're predicting, that all of a sudden it'll be a completely different technology. We'll use quantum computing or hyper-cooled cryogenic computing. I mean, sure, one could 15 years from now, but not 8 years from now. So I maintain that from a high-level view, we already know what the systems are going to be like for exaflops, because in just 2 or 3 years we'll have systems that are within a factor of 5 or 6 of exaflops. So we usually go up by factors of 10 to 20 each generation. Therefore, I claim, we know that there'll be evolutionary systems. Of course, there'll be different ratios of sizes of memory and exactly how many SIMD units you have in a node and so on, but not dramatically different. And most, well, essentially all of the additional power, just as was the case now, will be by the nodes becoming more powerful. Now, because of that, I believe that we don't have to worry about reliability any more than we have to now. And I mention that because many people have been very worried about exascale computers and beyond, saying, well, the failure rate will be such that there'll be a failure every 10 minutes, and so you won't even have time to save your data, so it's a disaster. But if you look at the causes of failure rates, the number of components and connections is the single most important one to worry about. The more connections you have, the more separate chips, the more failures you'll have. Well, with our current systems, we go 6 to 7 days in between any faults. Our next system at Argonne will have the same number of nodes within 5% of our current one. So why should all of a sudden it be so much less reliable? Well, one reason would be that if the feature size gets small enough, for the transistors within a chip, then you start to get problems with gamma rays and those kinds of problems. But that won't be the case in 2023, however, it will be a little bit later. So I'd say the good news is the users can start thinking today about the next 2 generations of systems that they have to write software for. And by users, I would include, of course, the people who develop the libraries, the middle software, and so on. And although electricity is an issue, we have seen that you can make substantial gains in operations per picojoule, as we are already seeing. And reliability won't be any worse problem, in my opinion, than we have now. So that's the good news. And what will these systems be used for? Well, certainly the grand challenge kinds of runs where some applications use the whole machine for many hours will continue to be a part of the application. But we foresee that a larger fraction, substantially, will be for ensemble computing, where throughput, uncertainty, quantification, validation, and verification, as was mentioned, are extremely important. And so being able to have time to solution for big ensembles of calculations is as good a reason as for having such a system as having one application use the entire system. So it can be one project using large fractions of the system to do many, many replicas of a calculation, for example, for uncertainty quantification. In situ data analysis is being done now, but is likely to be done more, because that way you avoid moving the data off, then having to read it back to analyze it. Why not analyze it with the same system or a very tightly coupled companion system? Workflows will be important with streaming data from experimental facilities or other simulations, analysis of data from community databases of both experimental data and simulation data. And so that means we have to add better encompassing software for the HPC computing ecosystem than we have now. But things like your collaboration is already doing much of those kinds of things. I'll go very quickly in the interest of time as to the why we think there'll be a lot of these ensemble calculations. So one project was looking at why is there a gene called NDM1 that is carried by some bacteria, and if the bacteria strain carries it, this gene is resistant to all the antibiotics that we have now. So it's a superbug. And so by using the advanced photon source, that very intense X-ray facility at Argonne, people were able to get the structure of the gene and the bacterium that carries the gene. And then they screen many, many compounds to see, well, why is it a superbug? Why is it that our antibiotics cannot attack it? And they found that having the structure, there was this large cavity, and then by simulation, they saw that this large cavity could bind all the known antibiotics, and once bound, the enzymes could cut the antibiotic, and meaning it inefficient. So we don't have a cure yet, but at least now that we know the structure and the cause for the superbug, then there's a chance of designing a different antibiotic that would be effective. In a different area that's relevant to petrochemical industry, for example, it was an analysis over 300,000 thermodynamically stable structures of some nanoporous materials called zeolites, and by doing analysis of many, many of those replicas, we found that many new compounds whose efficiency was much greater than known ones for ethanol water separation or hydrocarbon isodewaxing. So it's a way of finding things useful, in this case, for industry, by examining hundreds of thousands of possible combinations. The archives of simulation experimental data, of course, is not at all new, but I believe and hope we'll be doing more of that. I mean, I was involved many years ago in the virtual observatory for astronomy, and in which we made available many different collections of data from different kinds of telescopes and with different formats. And indeed, it led to new science results being discovered from those archives. Cosmology data is being stored that way, and it's a lot of data, petabytes. Of course, the climate community is doing that, earthquake simulation community, and even turbulence simulation. Bob Moser ran 200 million core hour project at Argonne and created a database that will be useful to people studying turbulence and biology and so on. And cosmology, again, the size is very large, over 1 trillion particles, and so this does run on all of Mira currently, and it's produced as much as 2 petabytes per week of data that will be made available to the international community in cosmology. And then in a few cases, there are unusual applications that will bring in HPC. So one is helping to design new cities or new neighborhoods of cities. This is part of Chicago. But the one I'd like to emphasize a little bit more is the one on the right. So this is the state of Illinois, which is one of the states in the United States where Chicago is. And what we're doing is working with mathematicians and the electric power industry in the state of Illinois to come up with a way to use wind turbine power more efficiently through optimization of a variable and unknown frequency source. Because do we know exactly when the wind will come up to a certain speed or when it will die down? And the electric companies have to have at least an hour advance notice if they're going to have to use their conventional generators to make up for the electricity that is no longer being produced by the wind. And so one of our mathematicians developed a stochastic optimization technique so you could be able to do that. So, and that works for the grid of Illinois. could work for the whole country if you have enough computing power, because, so it's a time-critical thing. You need to do it quickly, and that's why you would want to use a big computer. Of course, 10 years from now, the big computer will be something in here, and the size of this desk. So that's a kind of HPC application that I like to see because, well, it's good for society, and also it's different because of the data flows than you would expect. So you have to have regional climate prediction being done at a certain accuracy, and the stochastic optimization. Now, workflows. I'll use an example of a workflow called SWIFT, which I admit is developed jointly by Argonne and the University of Chicago. But there are many workflows, so I'm not claiming this is the world's best or anything close to it. It's a good one. So why would you need it? Well, if you want to do something like 1 million docking tasks where you're trying to do drug screening for diseases, you want to coordinate the execution of all those tasks in such a way that you can make sense of the results and execute them efficiently. And so Swift is general enough that it can use fairly flexibly both the big systems like Mira, Titan, and Edison at these big sites, but also the Open Science Grid, the NSF Exceed, and Amazon Cloud Services, other cloud resources, so the Google Compute Engine. So, and it can use scripts and local data, remote data, be hosted on many different kinds of systems. As is usual, as one tries to do bigger things, the original design of Swift was based on using one data flow engine to assign and control the tasks, and that works up to about 500 tasks. But what if you want to do 500,000? And so you do the usual thing. It has been generalized to you have 1,000 different engines that do the data flow analysis, and so you can do a very distributed evaluation. So one application of this was in near real-time analysis of experimental results for an experiment at the Advanced Photon Source. By being able to use Mira and a much larger analysis, you could do in 10 minutes what would otherwise at the local cluster at the Advanced Photon Source take 5.2 hours, so 30 times faster. And the reason this was useful is in the early minutes of a 3-day experiment, by streaming the data from the photon source to our system and doing the analysis, we found that no useful data was being gathered by the receptors. Having determined that so quickly, it was then possible to figure out what the problem was. Happened to be a cable problem. It was fixed within 2 hours, and then the rest of the 3 days could be used productively. So we don't usually use big computers like this for this type of thing, but now it's realistic to do it. And what enables it is a reasonable workflow software engine. So my view of exascale then, I've already given away most of the story. I don't think that exascale systems will be all that disruptive. Again, if you think of today's systems, basically they've been an evolution of systems of the late 1990s. So we have roughly 15 years of experience of systems where to get the speed you need to use thousands and then hundreds of thousands of cores simultaneously. Were they disruptive? True, but did we manage to make it through the problems? Yes. No, I don't mean to make it sound trivial, but it's not the end of the world, which some people believe. I may be proven wrong, but I'm just giving you my opinion. You will have to use very fine-grained parallelism for exploiting both kinds of architectures, a many-core, because of all the threads, or the GPUs. Memory size will change. Software engineering will be more important than before, because software will be more complex, partly because the applications are more complex. We can do things that are more physically faithful, and therefore it's a more complex application. We'll need new algorithms to some extent, but certainly new implementations of existing algorithms that are implemented more efficiently. And portability should be thought of from the beginning. And although I have a number of slides on that, I'm going to skip them, and this, you'll have them online if you want. And I already mentioned the error rates are not yet a major issue, but they will be certainly in the future. Now, the previous slide was my thoughts. If you want reports, they're online. There's a couple that you can look at your leisure. ASCII was a project that I was involved in 18 years ago, which was the Accelerated Strategic Computing Initiative in the United States. And what we were worrying about at the time, I just wanted to show as an example of why I'm not so worried about exascale, is we're worrying about much of the same kinds of things: scalable solvers, interoperability, and so on. In the year 2000, we came up with a prioritized list of the top barriers for going to petascale. And so data access for visualization, I/O, all these things should look pretty familiar. High-speed encryption was important because some of that work was classified. So, and the last thing I'll say, and then I'll skip the rest of the slides, are co-design. Well, certainly the systems we have today, many features of them are the result of companies, architectures, designers, working pretty closely with users at the national laboratories and universities. And so there has been substantial influence. Now, of course, there's a tension because the companies also like to make money and to be able to sell many copies of their products. And there aren't all that many scientists and engineers of the overall user population of computers. But still, one can influence those systems. But you have to do it years ahead of time, so we only have a couple of years to do that. So I'm going to skip the portability stuff, important as it is, and let me just close with this last slide. So the future HPC ecosystem, of course, is everything we're doing today, but because the data services, both in the type and the volume, will be increasing dramatically, we'll have a lot of things to worry about and things to add to our service models. I mean, one easy to identify thing is, well, how long should I keep online those 6 petabytes of cosmology simulation? Forever? Or is that something that maybe 5 years from now, there'll be a better simulation result? And then you wouldn't delete them, but at least you wouldn't have them online available to the world anymore. But those are things we don't have to deal with now quite that way. And then there's the access to all that data by an open community. How do you protect the data? How do you make sure that people don't use access to the data to then do nasty things? Those are important things. Some of it is policy and some of it is technology that we have to deal with. Now, you may think, the systems I've been talking about, well, how many of them will there be in the world, and does it matter to you? Well, all these systems are made up of building blocks. And the fact that the next generation will be based on Intel chips and IBM chips and NVIDIA, I mean, those are commodity products. So the systems you'll be buying and maybe having in your office, and to a smaller extent maybe in your laptop, will probably be using pretty much the same chips. And they will be having all those cores, just like even my iPhone has a couple of cores. So my hope is that it's actually a good thing, because people will be able to buy very small versions of the bigger systems, which would help the development of software, the integration of expertise, and the feasibility of doing different tasks like the data analysis fairly coherently with what goes on in the bigger systems or the experimental facilities, which will also be with clusters all around them and helping to control the experiments. So the easier integration of the new services into the ecosystem might result from that. Because the system we have now at Argonne, the IBM Blue Gene Q, the processor it uses is an IBM Power, but it's an IBM Power A2, which is not what you would get in your laptop or your server. So it's really a specialized, very specialized system. So hopefully, high-end HPC will become more easily and productively a part of the general HPC ecosystem. And that's my hope, because there are a lot of things that can benefit society and science by having all the tools available, instead of having to worry about, I can only do this, and only a few people will have access to the other kinds of analysis. Thank you very much.
So, although we're waiting for the coffee break, I think we have time for a few questions to Paul or some of the other speakers here today. So please, I open the floor for questions from the audience, or opinions, or disagreements, or
Oh yes,
whatever.
feel free to disagree with anything I said.
Joel. This, yeah, good.
So, Paul, is this thing on? Can you hear me? Yeah. There we go. You mentioned cache architectures getting more complex in the future. Do you believe that this is the direction that technology will take? Because if you have a chip of silicon, you have so much space to work with, and you can cram that full of semiconductor magic in one sense or the other, either cache architectures or just more parallelism with more shaders or more cores or whatever. So the direction of the GPUs is more parallelism, and the direction of the traditional processors is more cache. Do you believe that the direction will go more towards traditional CPUs with more cache architectures and less parallelism?
I'm not completely sure I understand your question, but in terms of caches versus memory, so we already have many levels of caches. That may not increase that much, but what I'm seeing is the addition of very high-speed memory on the same chip that has all the cores and all the network interface logic and so on. And so that can be, my expectation is that the user will have an option of using that memory, which, although sizable, will still not be as big as you would want. You could use it as a cache, or you can, but it can be a user-controlled cache, or you can just use it as regular memory. So let's say that, as an example, you might have, your L2 cache might be 4 megabytes. You might have this in-package memory, as some people call it, that's very, very fast, and it could be, let's say, 4 gigabytes, which, if you have 80 cores that want to use it, is not so much, 4 gigabytes. That's just an example. These are not real numbers, but then you'd have the regular DDR memory, which would be 256 gigabytes maybe. And so in that way, you can think of it as at least one additional level of memory. And then often we're talking about having non-volatile memory beyond the DDR, so that's 2 additional levels of memory. And so you have a unified address space, but you can manage it in different ways. So that's what I see happening. I don't know if that answers your question at all.
Sort of, yeah.
Sort of.
Okay, more questions? Yes, please.
Paul, you didn't address it, but the problem that's kind of exploding in our labs now is the need of storage. I mean, the size of the data set kind of increases faster than the need of computational powers to some sense.
Right.
And your slides had a lot of information about increased memory, increased disk size, and so forth. But I mean, the sets of data, the size of data sets now is so large that transporting data is a problem. Do you foresee some kind of paradigm shift in dealing with large chunks of data within the HPC community? For instance, the plans for Argonne National Labs.
Well, I agree that the explosion of data is here already and certainly will continue. Things like the LSST observatory, for example, will be gathering huge amounts of data every night. So the way we're addressing it is, one number that I did mention is, we'll be increasing our online disk base, to 150 petabytes, and then of course we've got tapes in the background. But of course that may not be enough.
So that doesn't solve the transportation problem.
Pardon?
That doesn't solve the transportation problem.
Right, and then as far as the transportation problem, well, we in the United States for the energy sciences laboratories and some universities, we have this 100 gigabit a second network, which is being expanded to 400 gigabits and maybe a terabit over the next few years. Now, that sounds like a small fraction of what you need, but in our experience currently, it may suffice. And as far as transferring the data, a lot of the problem is how long it takes, and that traditionally you have to manually supervise the transfer. So one way that we've addressed that is through software. So there's a Globus Online that you can start the transfer and it will monitor it for you. And so I know about a year ago we had a project that computed at Argonne, created 150 terabytes of data, which then he wanted to take back to Berkeley to analyze it. And so I called him and asked him, do you have any issues, or how are you going to do this? He said, well, actually we already did it 2 weeks ago. We just used Globus Online, started it up. It took about 2 weeks, but we didn't have to monitor it, and so it took place essentially by itself. Now, pardon?
You build machine infrastructure to kind of take care of the transportation.
Right, so I don't think that's the entire solution, but that's part of it, because there often are little glitches in the transfer, and then you have to restart. And it used to be you use a graduate student for that who gets no sleep. But
you don't foresee any new technology or paradigm shift in regards to how the data is?
well, the only paradigm shift, and isn't particularly new, is doing in situ analysis. And so, I mean, one trivial thing that we've been doing for 5 or 6 years at Argonne is that the data visualization and analysis engine, which is a separate computer, shares directly the same file system as our big compute engine. So at least you don't have to do any additional copies. So part of it is just the design of the hardware infrastructure. Part of it is the software, as I alluded to, with Globus being one example of a software that can help that. But you're right, I don't know how we will handle the volumes that will come out of LHC, not in the current run, but in the run about 10 years from now, and the LSST and so on. At Argonne, the advanced photon source is supposed to get something like a 40x increase in luminosity, and so correspondingly more data. So we worry about it. We're doing patches, I guess, right now, strategies that work for the moment. So I think people will be moving data less, and therefore making the big system easier to use is important, because you may want to use them closer to the data.
Okay, in order for everybody being able to get coffee, I think we should close this session now, and I suggest that we thank all the speakers with an applause.